All right, so here we go. An angle, pen? Yeah. An angle is determined by rotating a ray about its endpoint. So here's a ray, and if we rotate it, it's going to make an angle. So the starting position, or the side I just drew, is called the initial side, because it's the start. So that's the initial side of the angle. And then after we've rotated it, it ends is called the terminal side. So those are the two sides of our angle. The point, the end point of the ray is called the vertex of the angle. And where I just drew this thing, so when the vertex is at the origin and the initial side is on the positive x-axis, the positive x-axis has to be on that side on the right there, then the angle's in what we call standard position. So you'll see that in a lot of directions, standard position. So if I tell you to draw an angle in standard position, the first thing you're going to do is you're going to put your vertex in the origin, you're going to draw the initial side on the positive x-axis, and then you're going to wait to draw the rest until you figure out how big it is. So positive angles are generated by counterclockwise rotation. So if I want to draw a positive 30-degree angle in standard position, I have to start with my initial side on the positive x-axis, and then I have to rotate counterclockwise 30 degrees to get to my terminal side. I put a little mark in there, a little arrow on the top of that arc to show the direction that I'm turning. So positive angles always turn counterclockwise like that. Okay. Negative angles turn clockwise. So clockwise. Okay. And then we have one more word to deal with. Angles that have the same initial and terminal sides are called coterminal angles. So co meaning the same, terminal meaning end. So if I had a 300-degree angle, a positive 300-degree angle, that would go about to like right there, 300 degrees. It's in standard position because I started with the initial side on the positive x-axis, and then I turned counterclockwise. So if I wanted to be coterminal with that, I could have gone this way instead. If I rotated that way, I would be negative. And how far would I have to go so that I ended in the same spot? I'd have to go 60 degrees because the whole circle all the way around is 360. Okay, so we can figure out coterminal angles just have to start and end in the same spot. And oh wait, there is one more word after that. If the terminal side of an angle falls on the x or the y axis, then the angle is called a quadrantal angle. Quadrantal angle. So a good example of a quadrantal angle would be 90 degrees. Okay, 90 degrees, the terminal side is on the positive y-axis. 180 degrees would end on an axis. 360 degrees, 270, there's an infinite many number of quadrantal angles. Okay, here is our definition of radian. So 1 radian is the measure of the central angle theta that intersects an angle to the length of the radius of the circle. So if this guy's 1 unit long, then that guy is 1 unit long. It's also 1 is our arc measure, and that's 1 is our central angle in radians. Okay. So in other words, radians are ways to measure angles in terms of the length of the radius. An angle of 1 radian results in an arc with a length equal to the radius of the circle. So how do we find the circumference of a circle? 2 pi r, right? So if the radius is 1, then what's our circumference? 2 pi. All right. Now we're going to talk about revolution around a circle, radians, and degrees. So if I start out and I go all the way around the circle, that's 1 revolution. 1 revolution is 2 pi radians, which is 360 degrees. Hopefully your geometry teachers were sticklers about making sure you put that degree symbol up there, because if we leave the degree symbol off, it means radians. I know it's on the paper. But when you make a triangle, and I tell you that the angle is 30, if I don't say 30 degrees, it means 30 radians. Now we can't make a triangle with a 30 radian angle in it, but that's why the degree symbol is so important, because if it's not there, it means it has to be radians. Yeah, the degree symbol is written on the paper. So this next one says a half a revolution. So if I go a half of a revolution, how far is that? That's pi radians, because it's half of 2 pi, which is 180 degrees, which is half of 360. What if I go a quarter of a revolution? A quarter of a revolution is a half of a pi. So I write that as pi over 2, or 90 degrees. All right, I'm going to go to the one underneath that right now. 1/8 of a revolution. So if this was 1/4 of a revolution, then 1/8 of a revolution would be a quarter of the top, which is a quarter of a pi, or pi over 4. So half of 90 is 45 degrees. Okay, I'm going to make a new circle. If I make my new circle over here and I divide it into 6 parts, 1, 2, 3, 4, 5, 6 parts, then 1/6 of a revolution is 1/3 of the top. The top was pi, so 1/6 of a revolution is pi over 3. Which would be 1/3 of 180 degrees, which is 60 degrees. One-twelfth of a revolution would be half of a 1/6 of a revolution. So half of pi over 3 is pi over 6, and half of 60 degrees is 30 degrees. So pi over 6 is 30 degrees, okay? We'll go over more detail next time how to convert between degrees and radians, but where you draw these, it all makes sense. So reference angles. If we want to turn everything into right triangles so that we can do SOHCAHTOA, and we have just random right triangles, if I've got one angle in a triangle, then my other two, they have to be acute. There's no possible way to make a right triangle where one of the other angles is bigger than 90, right? So they have to be acute angles. You can't have a right triangle with a negative 20-degree angle. It has to be between 0 and 90 for the other angles to make a right triangle. So what we do to kind of fudge it so that we can turn everything into these right triangles is we create reference angles, okay? So the values of the trigonometric functions of angles greater than 90 or less than 0 can be determined by using their values at the corresponding acute angles called reference angles. So we're going to start out, let theta be an angle in standard position. Pretty much whenever we're drawing an angle, we start out by drawing it in standard position. its reference angle is the positive. I'm going to put in acute also. It's really acute implies that it has to be positive, but I'm writing positive just so we realize it's got to be both positive and acute. Angle theta prime formed by the terminal side of theta in the x-axis. Okay, so we didn't have a quadrant 1. Oops. So I'm going to come over here and I'm going to draw a quadrant 1 angle. The reason that there's no quadrant 1 angle on there, if we're starting out in standard position, I'm going to start out with the positive x-axis. If I am in quadrant 1, then that means that my terminal side is going to land up here. So when I draw an angle, my theta right here will already be the positive acute angle between the terminal side and the x-axis. So for this one, my original angle and my reference angle, which I often call it theta r, they're calling it theta prime. I lose primes when I write, so I write little r's instead. So the angle and the reference angle are the same angle. Okay. Let's look at the other ones. So for each of the other quadrants, quadrant 2, 3, and 4, I was in standard position, so I put all the positive sides, or the initial sides, on the positive x-axis. Now it's going to depend where my terminal side ends. If my terminal side lands over here in quadrant 2, then that means that this angle right here was my original angle theta. My reference angle is going to be formed between the terminal side and the x-axis. So this little piece that's missing to get to 180, that is my reference angle. Okay, so now it's an acute angle. If I'm over here in the second quadrant, or sorry, the third quadrant, and I turn starting at the initial side, going all the way around, that's my original angle theta. That angle is going to be bigger than 180 degrees or bigger than pi. So in order to make it an acute angle, I want this piece right here that goes between the x-axis and the terminal side. It's going to be acute. To make it positive, I have to make my little point turning towards the terminal side for this one. That little piece right there is my theta r, or my theta prime. That little piece is the reference angle. So it's how much I went over 180 or how much I went over pi. So if I land over here in the fourth quadrant, my original angle theta would be going all the way around the outside there. That's my theta. My reference angle is between the terminal side and the x-axis. So it's just this little piece left here that I had to go to get to 360 or 2 pi. So reference angles, if I in the first quadrant, then my reference angle would be here, and I could draw a right triangle like that. If I land in the second quadrant, then my reference angle would be here, and I can draw my reference angle. If I land in the third quadrant, my reference angle is there, and I can make a right triangle. And if I land in the fourth quadrant, my reference angle's there, and I can make a right triangle. And they call that a bow tie. The reference angle is always positive, it's always acute, and it always goes to the x-axis. So if you were dealing with 4 points that were in the same family rectangle right here, this arc measure or arc length would be the same, and all of these would have the same reference angle. Okay. So here are some examples where they're asking us to draw the angle in standard position and then determine the reference angle. So we can only determine the reference angle if it's not quadrental. If you're a quadrental angle, you're not going to have a reference angle because we can't draw two 90-degree angles in a right triangle, and we can't put a 0-degree angle in a right triangle. So quadrental angles really don't have a reference angle, right? So this one we're trying to draw a 405-degree angle. So when I start out, if I'm going to be in standard position, I need to put my initial side on the positive x-axis with my vertex at the origin. Okay. Now I've got to turn 405 degrees. It's positive, so I'm going to start out, I'm going to turn counterclockwise. 360 degrees would be going all the way around. Now 405 degrees more than 360. So once I get to 360, I need to go another 45 degrees before I draw the terminal side. So that's my angle theta right there. All right. So the terminal side makes one whole revolution of 360 degrees plus 45 degrees more. So if I went 45 degrees more, that means this little piece right here is 45 degrees. And that's what my reference angle is. Okay, the 45 degrees extra that I went would be the positive acute angle in the between the x-axis and the terminal side. So my reference angle is 45 degrees. Okay, so example B here is negative 65. In order to be in standard position, I've got to make my vertex at the origin, my initial side on the positive x-axis. Because negative 65 is negative, the terminal side is clockwise from the positive x-axis. So I'm going to turn clockwise about 65 degrees. So that's my angle theta right there. It's negative. My little arrow points like I'm turning in the clockwise direction. So whereas my angle is negative 65, my reference angle has to be positive. It has to be positive and acute. So I was already between the terminal side and the x-axis, but I wasn't positive. So my reference angle is the positive 65 instead of the negative 65. Pause the video while you try C. Okay, so to draw 150, I put my initial side on the positive x-axis. I turn counterclockwise 150 degrees. So to get to 150 degrees, I am 30 degrees short of 180. So my reference angle is the 30 degrees that it would take to get to 180. All right, we're going to skip D. I'm going to have you come back and try that one in just a second, and we're going to do E. For E, this is 5 pi over 6, which means it's in radians. So I'm going to start out, and I'm going to make my initial side, just like normal, is going to be on the positive x-axis. I'm going to be turning counterclockwise because I'm positive. Okay. If I went all the way to the left, to the x-axis again, that would be pi, because that's half of going all the way around, which was a radius of 2 pi, or a circumference of 2 pi. So this pi is how many sixths? Pi would be 6/6, right? Because 1 pi would be 6/6 of a pi. So if I need to go 5/6 of a pi, that's going to be right about here. So my theta is 5 pi over 6. I could also make little marks. That would be 6 little sections. I need to go 1, 2, 3, 4, 5 of them. How many are left down here? 1 of them. So my reference angle is pi over 6, or the 6th that I was short to make it all the way around. Okay, so that's pi over 6. I want you guys to try the rest of them. Remember, if they land on a quadrant, then they don't have a reference angle. So you can pause the video while you check these remaining and come into class with any questions.